Okay, I don't know why I'm wearing my shield because there are no students in the room, but and my other screen went blank, of course. Everything was working well. The other screen is totally gone. So, don't understand that at all, but hopefully you guys can still see me here, right? Am I correct as you can still see me, anybody?
Yeah, we can still see you.
Yes, you can. Thank you. The other screen, if you've been in the room, is the second screen. The second screen is just totally blank. I don't know what happened to the computer. But it seems to be gone. Okay, we'll have to get that fixed, but I can't worry about that right now. The recording should still be working, I think. Aha, we have a student coming. And, okay, all right, first, from the last couple of days, we talked about having an exam. I will put on Blackboard today. It will be due next Wednesday. I have a second student coming next Wednesday, and we will be having another test on chapter 6 is coming up next week, but we aren't done with chapter 6 yet. And then we will have a final, which will be on Monday. Okay, so I presume you're all aware of that information. Secondly, I gave the people who were in the room on Monday a copy of 6.1, and there are some typos on that. On Blackboard, we have a new 6.1, which for the typos I found, they have been removed. Now, one of the problems is there's an important one, and I think I even talked wrong about it because I put it up on the board copying the pages. I will show you the pages in a minute, but when you do improper integrals, you might be talking about an integral that looks like that, or sometimes, not for us, the integrals might have an infinity on the bottom, or they might have infinities both places, top and bottom. I assume you guys can see me. As I said, I've got one blind screen today because it just went off. So I'm assuming you can see what I'm writing on the board. I don't know if you can fix it, it's fine, but it's dead. I don't know why it's dead.
Yeah, we can see it.
Turn the machine off and on, so on. So if one of you wants to try to fix it, you can. But anyway, point is, this is the kind of stuff we have. Now, for us, we're not going to have this one. We're not going to have this one. We're going to have this. But the other day, and in my notes, there are some errors about the A here, because for an old person like me, when I proofread it, I saw 0 instead of A, evidently a couple of places. So for us, for Laplace transforms, we're going to have a 0 here. Okay. And improper integrals are defined for other places, but we're going to have a 0. So our functions f that we're going to have are going to be defined from 0 to infinity. And I wrote a closed interval here. They might be defined only on an open interval. But anyway, they go from 0 into infinity. And they go into a set. In other words, the range is a set of things there are functions, and those functions will be defined from some a to infinity, okay? So the a comes in because the functions f are going to be of exponential order, and for that, there are three things that happen. You have an a, and you have a k, and you have an m, which we can talk about a little bit later. But the problem is you don't want to confuse, as I did in the notes that I handed out the other day. I had some A's down here when I should have had zeros. How'd it come back? What happened? Okay, it's back. It just happened?
Yep, it's happened.
Just happened, okay.
And it wasn't when I was shaking the mouse or anything.
Okay,
Oh, no.
so it just happened and it wasn't, we're back in Zoom. So it wasn't the machine went off, because if the machine had gone off, it wouldn't have come back. So who knows? Okay. So anyway, some things like that. So on page 2 of those notes, and I'm going to put the notes up on the board for you guys at home, up on the screen. There was a definition which is wrong, and it's an important one because it's a definition of Laplace transform. So I'm going to put up the share screen here so you can see what I'm talking about. So this is section 6.1, and the first page we talk about improper integrals. The second page we talk about some of the tests, and then we bring up the exponential order and the existence of Laplace transforms, and the exposition, which is toward the bottom of the second page, that before on Monday the integrals had a at the bottom. And so for those of you here in class, you see that there's the exposition, you find that place over here. This is an a, that should be a 0. Okay. It should be an integral from 0 to infinity. As I said, I just didn't catch that. And the other day I actually wrote it on the board, but it was wrong because we can talk about improper integrals from 5 to infinity, but for Laplace transforms, it's always going to be from 0 to infinity. Okay. So that's important because that can mess you up. So that has nothing to do with the a, which is involved with exponential order, which I defined right above there. So there is an a, and it's basically talking about as long as the functions graphs are below an exponential function, that's when we can integrate. And so the a comes in terms of convergence of the integral, all right? And that's because we have an s that's involved in integration. And when you change the s for various s's, like if you would make the s negative in the definition, you see the exposition there. If you made the s negative, that would make the exponential positive, and that's going to diverge. So the a that comes into talking about how fast the f gets big is involved with when the integral is going to converge, but not involved with the definition of the integral, which always will have a 0 at the bottom. Okay? I just don't want you guys to get confused back at it because I wrote it wrong and even said it wrong, I think, in the other day. So these are the things we're going to deal with. And basically what we do in these notes is stick different functions into this integral and see what we get. Okay. Now, the thing we get is, the general statement here is about what we call Laplace transforms. So we're basically talking about a function, and I don't mean capital F now. I'm talking about a function that takes functions little f and makes them functions capital F. So the function I'm talking about, called the Laplace transform, is a transformation from one type of functions to another type of functions. Okay, it's not like graphs in calculus where you have a domain is numbers and the range is numbers, and you have some function taking you, like if you square things, you're taking numbers to numbers. You're taking 5 to 25. Well, we're taking a function and sticking it in this transformation, and out will come another function. Okay, So the notation is more complicated. That's why everybody screws it up. And historically, they didn't have functions, and therefore they had variables, and they messed up, and they made notation that made it look like they thought it was. It's not how it was. They didn't know that. They made up notation because they're very smart, and we still hold on to some of that notation, even though it no longer should be used. But people don't know that, and some areas of the world are still in the 19th century mathematically, and so they still use that. Okay, anyway, so what I write here at the top of page 3 is what I just ended up saying. The Laplace transform takes you from a set S, that's a set of functions, to a set T, that's a set of functions which I tried to put on the board a minute ago. And so the technical correct thing to say is L of little f is little g. That's like saying if L was squaring numbers, that would be saying like L of 2 is 4. Okay, except it's not 2 and 4, it's functions. So, and what is the G? Okay, well, notice that the G is the capital F here. So I should have had an F here as another typo I just see. The G here is the function that we've been calling F. So I probably should have put a F here, capital F, and then left this alone. Okay, well, sooner or later we'll get all the typos out of here. Anyway, the function L is a linear function. That means when you add functions and then transform them, you could have transformed the original function first and then added them. When you take a function and multiply it by 5, you could have, and then transform it, you could have transformed the original function, and after you get done, you could have multiplied by 5. So that's what linear is about. And these things are linear. Integrals are linear. Derivatives are linear. Okay. And Laplace transforms are linear. So the stuff on page 3 is trying to justify all of that. And then I talk about the Buse notation, which we've more than briefly covered. So I want to talk about what's on page 5, the Laplace transform of a derivative. Now, and if you, I guess everybody's got, they can see that on the screen, so I don't have to write it on the board. But basically, if I want the Laplace transform of a derivative, that would be sticking f prime. So right below the word proof, you'll see an integral. The integral is from 0 to a. The reason it's from 0 to a is because later we're going to take a limit, because it's actually 0 to infinity that we're interested in. Okay, I have e to the minus st, which you have in every Laplace transform, and I'm doing Laplace transform of the derivative, so that's why f prime is right there. Well, this is a setup for integration by parts. Okay, remember integration by parts kind of switches a derivative and an antiderivative around. And so if I let u be e to the minus st and dv be f prime of t, then v is f of t and so on. And so you do integration by parts and you come up with this. This is the uv. When you have definite integral, you got to stick in the stuff, minus the integral of v du, which is the rest of this. And when I differentiate e to the minus st, the u, I'm going to get a minus s out of it. And that's where you'll see a minus s right there. So this is a straightforward integration by parts. And then you stick the a and the 0 in there and see what you get. And so you get this two things in an integral with an s outside, because the s is not the variable. The s is the t, which is the variable of integration here. You take limits. The s is not involved with the limit. You take limits, and what happens? Well, this e to the minus sa is going to go to 0. And so that's going to drop out. This f of 0 is just a constant, so that's going to stay there. And what we do is replace this thing with infinity, and that's why you get the, this is the original, and it's s times the Laplace transform minus f of 0. So all that is a simplification because parts of it become 0. And so the Laplace transform of the derivative is s times the Laplace transform of the original function minus whatever f of 0 is. That's going to be important for us later. And then we do the same thing with the second derivative and the third derivative and the fourth derivative. And generally for us, we've been studying first order and second order differential equations. So for us, we probably don't need to know more than the second derivative transformation. Peyton is trying to get in, and I've let him in twice. He really wants to get in, so he must be having trouble. So Peyton, if you're there now, I'm trying to let you in every time you need to be let in. I don't know what the problem is, but okay. So we have formulas for the second derivative and the third derivative. Now, I wrote it in terms of the nth derivative, but if you want to see what it is for the second derivative, you put 2 in for n, and that will be right down here above the word proof in the middle of the page. The Laplace transform of the second derivative is the square of s times the Laplace transform of the function minus s times f of 0. And if n is 2, this s to the n minus 2 is not there. And so you would, this becomes 1, and you'll have this, but you wouldn't have the rest of this. And we're going to see some more of these things. But you need to write down the second derivative so you know what it is, because that's generally the most derivatives we're going to deal with. Okay? So now the rest, several more pages, is actually to do improper integrals where we stick various functions into the integration to see what we get. And in class the other day, we took the Laplace transform of the function 1, and we found out we got 1 over s. And so that's a conclusion here. I actually do it for you here. This is what was on the board the other day, or what was attempted to be on the board the other day. Okay, and so the Laplace transform of 1, and so the proper notation would be the Laplace transform of the function 1 at s is 1 over s. Okay, then what do? We transform the exponential function, and the exponential function is going to be of exponential order, of course. Okay, and if I have an a here, it turns out that that a turned out to be the exponential order a. And so that means the Laplace transform is going to be valid for s greater than that a. So if I had e to the 2t, Laplace transform works for s greater than 2. If I had e to the 10t, it's going to work for s greater than 10. All right, now remember, that's not the function. F is defined from 0 to infinity. It's capital F, or the Laplace transform of little f, which is defined on the interval starting at a. And so in this thing, we're producing a table, really. When you transform e to the at, it becomes 1 over s minus a. That's what this conclusion is. And so here's the proof of it. And so what you have, and these are actually problems in your notes that I've written out for you. What I'm doing is developing Laplace transforms for all these functions. Now, as soon as you get to the sine function, notice it's more complicated, because to do the sine function, you have to do 2 integration by parts, because when you have an e to the minus st and a sine, and you do 1 integration by parts, you'll get an e to the st with a cosine. You have to do another one, and you have to take it to the other side and divide by 2. You may remember how you did that with such things. So the sine's a little more complicated. I want you to have it. And so what happens to the sine function? The sine of at becomes a over s a squared plus f squared. And here, one can find the Laplace transform for cosine. Okay, and you should do that, by the way. You should do this kind of work to see what it is. But I said, instead, let's do something else. Okay, want to do an alternative. It assumes that dealing with complex numbers here is still legitimate. Now that's going out of our class, basically, and saying if we were in a complex analysis course, we could do the same Laplace transforms with complex numbers. And it turns out that will give us a different way to deal with cosine. So what is that different way? Well, the cosine can be written as e to the iat plus e to the minus iat over 2. It's like a hyperbolic function. except it's got an I in it. And so if we treat that as if these are all real numbers, this is cheating because we haven't verified it, then we could transfer this e to the I alpha t over, and remember, so because above here I did e to the at, you may remember, e to the at was 1 over s minus a or something, right? So if I do that with complex numbers, assuming it's legitimate, and that's, I don't know what happened there, and that's a big assumption, we treat them like reals, we transform them, and it turns out you get the same answer, okay? So that's not a legitimate process, but I thought I would throw it in there because we could make it legitimate if we spent some time in complex numbers. Okay, now, so what have we transformed so far? We've transformed exponential functions, we've transformed sine and cosine and constant functions. So the next one is to take t, all right? Now, why are we doing all this? Well, we've already seen that we can transform a derivative, and we can transform a second derivative, and we can transform numbers, time functions. What do we have a lot of trouble with in dealing with, before we did power series, in dealing with solutions? We had homogeneous equations, if you remember, in second order, and that was when you had a 0 on the right-hand side. And those were easy to solve because you just found the root of a quadratic function and found 2 roots, and you dealt with it, okay? Now, where did it get harder? It got harder when you had a right-hand side that was not 0. And what were the right-hand sides we dealt with? Sines and cosines and exponential functions, things like that. Well, if we're going to use Laplace transforms to transform the differential equation into a different world, if the differential equation has a right-hand side, like cosine, we're going to have to be able to translate the cosine. That's why, so far in this stuff we drew in today, I translated the cosine and the sine and stuff, because when we get to differential equations stuff, we will need to transform those functions. Okay, well, one of the things we also have is occasionally is t or x. We got to be able to transform that. So t or x transforms to 1 over s squared. T to a higher power. Now, this gets more interesting a little bit, I think. You may think it gets less interesting, but what do you know? So if t to the n is an integer, like t squared or t to the 10th, then the Laplace transform involves the factorial. So if I had t cubed, the Laplace transform of the function t cubed, and of course it's not the function t cubed, you see I just abused notation, it's the function which cubes. If I transform that function, I will get 6 over s to the 4th is the transform. Okay, so it's factorials in here. Now, so I prove this by mathematical induction, and then we get to hyperbolic sine and hyperbolic cosine. But you remember the hyperbolic sine can be written as exponentials. And so what we can do, instead of doing any more improper integrals, is we can take the L of the hyperbolic sine and write it as the linear combination of 2 functions and split it up and do linear combination of each of them and then do the arithmetic and put it back. That's what you see in the middle of page 9. And so same thing with the hyperbolic cosine. Okay, so, well, you may remember that we sometimes on the right-hand side had an e to the 2t times sine of 3t or something. So I'm transforming that now. It gets a little worse. But what you're going to find out here is, and you may not be familiar with this enough yet, but this thing here on page 10, I think it is page 10 for everybody in class here, Yeah, the proposition 19, the Laplace transform is B over S minus A squared plus B squared. Now, a little earlier, and I don't want to make you dizzy with me switching it back, but if you remember a little earlier, we transformed the sine function. We did sine of AT, the sine of AT, okay? What did the sine of AT become? It became A over S squared plus A squared. So if I had done the sine of BT a few pages back, it would have become B over S squared plus B squared. When I multiply with an exponential function, what happens? The transform shifts. It's like the sine, but it's S minus A because of the exponential. Okay? And so when I multiply a function I've previously taken the Laplace transform of by an exponential function, it's going to shift it. It's going to shift it by the A. So anyway, and in this one I did the complex thing again, and so on. So we have that. And so now I'm also transforming hyperbolic signs. And so you'll notice all these E things are all shifts of what we already did. So I hope you go through these. I decided to do them for you rather than make assignments because there's several reasons. I want you to get it right. For one, two, is get to the end of the semester. I don't want you to be bogged down for 2 weeks trying to do these integrals. So hopefully it'll help you. But all of a sudden we get to a new deal. And that's called the gamma function. Okay, now the gamma function is defined at the bottom of what you see on your screen. It's actually the bottom of page 12. The gamma function is a new function that maybe you've never seen before, I don't know. It's a function defined as an improper integral. And it's defined for different values of P. Okay, the P is fixed, but the P could be 5, or it could be minus a half, or it could be the square root of 7. Okay, and what we're trying to do is to generalize the power of the x in the integral. Earlier, we talked about x to the n. We actually said t to the n, but x to the n, where n was an integer. Remember x squared, and it was t squared and t cubed and so on. We had a formula for transforming t and t squared and t cubed. Well, what if it's t to the 1/2? How do you transform that? Well, if you remember back a while ago, I said if I transform t cubed, it would become 6 over t to the 4th or something. Well, that 6 is a factorial. So if the p is a positive integer, this function we will have already sort of talked about. Now, this function I'm giving you here is missing an s. Notice there's no s in it. So it's missing something. But the point is that p can be square root of 7. Whereas earlier when we transformed x to the n was like 5 or 2. When it's like 5 or 2, the Laplace transform is factorial over something. But if the power is a half, there is no such thing as a factorial. Therefore, it turns out the gamma function generalizes factorial. So I'm going to skip to the bottom of the notes that you had, more or less the bottom, and show you page 16. 16 says, if I'm going to translate t to the p, Laplace transform of t to the p, where p is anything bigger than -1, then instead of factorial in the numerator, you have the gamma function in the numerator. So in other words, when people wanted to transform powers that were not whole number powers, they had to develop a new thing, and it's called the gamma function. So gamma function becomes part of one's repertoire for elementary functions. The new ones you may have had when you had trigonometry were the 6 functions assigned to cosecant. And then you did hyperbolic functions. You introduced 6 more. Then we did inverse functions. You have 12 more and so on. So you end up with about 30 functions. Well, here's another one. It's called the gamma function. And but you can't define the gamma function until you have improper integrals. And this is why you didn't have it in high school. Okay. But the gamma function is another function that we have. It's defined in terms of an improper integral. The Bessel function that we sort of briefly touched on, that's defined as an infinite series. And so you couldn't talk about that function until you had infinite series. So some of the functions that come up in modeling phenomena, besides trigonometry and logs and exponential functions and polynomials, we also have things like the gamma function and the Bessel functions and some others that people learn about. Well, this is about the gamma function. So I skipped several pages. What have I skipped? This is a brand new function, the gamma function. So I skipped several pages about the gamma function. So now I'm going back in the notes to page 15. One of the interesting things about the introduction of such things with a gamma function, you can prove the integral, and I noticed a typo here, of e to the minus x squared is the square root of pi over 2, which is an interesting formula. And before that, I deal with various gammas. Gamma function of a half, what is it? Turns out to be the square root of pi. And so we have a new function, and what I'm going backwards now, I'm going page 14 and 13 and stuff. The point is, what I'm doing here is introducing to you, or for you, the gamma function. And so the gamma function is actually defined on page 13 at the bottom, definition 25, and I start doing properties. And if you look at property 1 in number 26, that looks like factorial. The gamma function of p plus 1 is p times gamma of p. Now, it doesn't look quite like factorial because the p plus 1 factorial will be p plus 1 times p factorial. But notice it goes down. So the gamma function of p plus 1 is p times the gamma function of p, which would be p times p minus 1, the gamma function of p minus 2, and so on. So it looks like factorial. Okay? And if the p happens to be a whole number, it is factorial. So the gamma function generalizes factorial, and it's used when you want to raise functions, or raise something to a power other than the square root, other than a whole number. So enough of that. That's what's in those notes so far. Okay. And so what I want to do is go to the second section of the notes. So what I'm going to have to do is get out of the share here and take a second to try to translate over, if I can get back to section 2, which is in course materials. And then, so I've done that now, and then get back to the share screen. So, okay. So for those of you at home, welcome to section 6.2. And for those of you who are here, I've got to welcome you to section 6.2 by giving you section 6.2. I don't think I gave these out today. So this is section 6.2 for those of you who are here. Okay. So change the game. So what we're going to do here is we want to take an example, and this is example from the book, but I want to see how we're going to use Laplace transforms in differential equations class. So first problem, I have y double prime minus y prime minus 2y equals 0. Now, This is a second order ordinary differential equation with constant coefficients. Do we need to nuke this thing with Laplace transforms to figure out the solution? The answer is no, because with constant coefficients, you remember you replace this with r squared minus r minus 2 and you factor and so on, right? So we can solve this with chapter 3. So the purpose of the example is not to solve the equation, it's to show you how you use Laplace transforms. So in order to take the Laplace transform, we assume we have phi as a solution. And so I wrote here L of phi of s is y of s. So I'm saying the Laplace transform of the function phi. Now, the function phi is going to have t's in it. The function y is going to have s's in it. Remember the other day I told you that the world we start in is a t world, the world with variables, the world we end up in is an s world. So I'm going to transform the right-hand side, L of 0 is 0, and then I'm going to transform the left-hand side, and it's a sum or difference of things, and so because it's additive and homogeneous, I can replace this with L of phi double minus L of phi prime minus 2 L of phi and figure out all three of them. So you look back at the notes from section 6.1 or something else we haven't had a chance to talk about yet, and that is on page 252 in the book you have is a list of all those things I put in 6.1. In other words, there's a table of Laplace transforms. Okay, so all those ones I developed are in the table, plus a couple of things we didn't develop yet. Okay, but if you look at that table on 252, you'll see the Laplace transform of 1, Laplace transform of e to the at, and so on down the line. And so 252, that will be like a cheat sheet for you when you do a Laplace transform test. I haven't decided yet how much of the book or notes I'll allow you to use, but no matter what we allow you to use or not allow you to use, we'll provide you with a table like this so that you can quickly see what the Laplace transform of something is. Okay. Anyway, so either reading the table or looking at section 6.1 notes I gave you, or the book, the section, when we transform a second derivative, it becomes, and I'll use a cursor here, it's s squared y of s minus s of phi of 0. Remember a while ago when we did it, it was f of 0 minus phi prime of 0. Now, that's what the Laplace transform is of the second thing. In the notes, it was the nth power, and you didn't see that exactly, but this is exactly what it is. So you can learn right there, this is what it would be when n is 2. Minus the Laplace transform of the derivative, that's this stuff over here, and minus 2L, and that's just Laplace transform. So what I'm going to do is collect terms. When I collect terms, I get s squared minus s minus 2. Now, that's our old friend, the characteristic equation. Remember? If we didn't know about this, we'd be doing r squared minus r minus 2. Well, boom, it's the same problem. And so out of this Laplace term comes s squared minus s minus 2. Okay? But it's got some other junk here too. It's minus s plus 1. That equals 0. So now we solve. So we take the minus s plus 1 to the other side, and we take s squared minus s minus 2 in the denominator. And so we have capital Y of s is s minus 1 over s squared minus s minus 2, which we factor the denominator, and we figure out partial fractions. So what I have is s minus 1 in the numerator and s minus 2 times s plus 1 in the denominator, and I divide those two up by partial fractions. So the 1/3 and the 2/3 means I'm skipping some stuff here. You have to find out the 1/3 and the 2/3 by partial fractions. And once I've got that, I can do an inverse transform. If I know what 1 over s minus 2 transforms back to, And if I know what 1 over s plus 1 transforms back to, I can write down the answer to the original function. Well, 1 over s minus 2, you'll see I have an L inverse there. The inverse Laplace transform of 1 over s minus 2. And notice that's a function of t. That is e to the 2t. And the inverse transform of 1 over s plus 1 is e to the minus t. So what I'm doing is going to that table and going backwards. Well, we already know the roots of the characteristic equation were 2 and minus 1, and so we already know the solutions are e to the 2t and e to the minus t. But this is an example, an easy example of the game we have to play. And so what you'll notice is Laplace transforms gives you an algebra problem to solve. And you try to split the stuff up so that you can transform the stuff back by the table. In this particular case, we had to use partial fractions. But the whole idea of Laplace transforms is to replace the differential equation by an algebra problem. You manipulate the algebra with some direction in your mind as to how to do it, and then you invert the Laplace transforms of what you get. That's the game. So, second problem, harder problem, second example. Suppose on the right-hand side we have sine 2t, you see? Now, again, could we do this problem without Laplace transforms? Of course we could. This time, r squared plus 1 is the characteristic equation. That gives you two complex roots, cosine t and sine t. So I already know two solutions of the homogeneous equation. How would I find the solution of the non-homogeneous equation? Remember, you have to find 1 is equal sine 2t. So I either could use guessing, which would be to make it a sine 2t plus b cosine 2t and find out what a and b are, remember? Or variation of parameters. We have two methods for doing that. Okay, well, how are we going to do it here? We just transform everybody. And the Laplace transform of the sine of 2t becomes, as you see in the bottom of page 1, 2 over s squared plus 4. And now we do the same game. We translate everybody and we see what we get. So you get this mess here. We get y of s, we get 2s cubed plus s squared plus 8s plus 6 over s squared plus 4 times s squared plus 1. So what do? Partial fractions again, a little bit harder because it's 4 letters instead of 2, and so on. You play the game. I try to work it out for you on page 2 of these notes, and you find out that a is 2, c is 0, b is 5/3, d is minus 2/3. So you write the y of s as the sum of those two things, and then you try to translate it back. Well, I said by using the table in a reverse manner. Now, I cheated a little bit because really, it's not at this moment in the middle of page, whatever that was, 2 for you guys here. What I have in a numerator is 2s plus 5/3. That's not in the table. But 2s over s squared plus 1 is in the table, and 5/3 over s squared plus 1 is in the table, more or less. 5/3 isn't there. So I have a common denominator, so I split the numerators. So although it doesn't show you there, there are actually 3 things there instead of 2. So I translate 3 things back, and I get cosine and sine and another sine. Okay. Now the cosine and the sine, those were the answers to the homogeneous problem. Does anybody notice something else that happens? What if we were trying to do this the old way that we had? If I did this problem with variation of parameters or guessing, what do I do at the end? I make a general solution of the homogeneous problem. That involves a number times a sine and a number times a cosine. How do I find out what those numbers are? I stick in the initial conditions. After I have solved the problem, I stick in the initial conditions. With Laplace transforms, I have put the initial conditions into the problem. At the bottom of page 1 there, you will see I have, by the time you get to the top of page 2, I have put in the initial conditions, because one of them is phi of 0 and the other one is phi prime of 0. So in Laplace transforms, we substitute the initial conditions early on. So by the time we get done, we have the general solution without, at that time, sticking in and solving for the coefficients. So it's the same process in a different order. Okay, and that's important. Okay, now example 3. I said here, I'm leaving this for you to work out. It's also completely written out in the text. But what is this one about? Well, it's fourth power. We skipped that chapter, remember? But can you do the problem without Laplace transforms? I hope you can. That would be r to the fourth minus 1. That's the characteristic equation. What's r to the fourth minus 1? How does it factor? It factors to r squared plus 1 times r squared minus 1. The r squared minus 1 becomes r plus 1 times r minus 1, and the r squared plus 1 becomes r plus or minus I. And so I get 4 answers: cosine, sine, e to the t, and e to the minus t. 4 answers. Then I make up a linear combination. That would be like a times cosine plus b times sine plus c times e to the t plus d times e to the minus t. And then I would stick on my initial conditions, which in this case, some of them are 0 and stuff. Okay. Well, instead of that, you guys are supposed to do Laplace transforms. And all this is a practice on saying, what if I'm transforming the fourth power? Then you got to go back and read that formula again. Okay, but the formula sticks in all of these initial conditions. So you ought to be able to do this. I left space for you to do it, you see. And if you want to do it on page, of course, you can't, you want to scratch on the computer. And we have another example. We're beginning to run out of time. But what in the world is this? You may remember what the sine function is. The sine function is an alternating series with odd powers and odd factorials. And so another thing we could do here is stick the series in instead of transforming. We could have put the sine series in here and then done it part by part. Now, there's some assumptions here. I said the interchange of the order of integration and summing series below requires justification, which we shall assume has been done. So you just blindly go on. This is what people did in the 18th century. They didn't have any of these theorems as to when things, or you could and when you couldn't do stuff. They just did it. In this particular case, if you assume that instead of using the sine function and our table would jump us to the bottom here already. But if you replace the sine function, how do we do this problem? In the notes in 6.1, you didn't do it, I did it. We did integration by parts a couple of times. We could have stuck a series in here, evidently, if we can believe the integral. See, this gets into stuff that you guys, the improper integral of an infinite series. You never dealt with that. So what I did is the improper integral of an infinite series, that's the infinite series of improper integrals. We don't know that. That has to be proved. But once it's proved and you do that, you can make a series of integrals and do each one of them and you come up with it. So this is just an example that's in the book. I thought I would leave in here. And the next thing, and we'll leave this for Monday or Friday or whenever the next day is, notice what I got here. In other words, I got a Laplace transform. Can you differentiate it? Well, you guys have, when we differentiate an antiderivative, you get the inside. But I'll bet you've never differentiated an improper integral. You see, except the improper integral is not what the derivative involved in. The derivative is involving with differentiating the S part. The S is hidden inside there. And so it turns out that the derivative of the Laplace transform is the improper integral of the partial derivative of the integrand with respect to S. And that's a new twist you haven't seen before. So anyway, we got some more notes to go through on Friday. It goes up to page 6. And then on Blackboard, you will notice that there's a section 3 and a section 4 and 5. And once we do those notes, we will be done with the material of the course. That doesn't mean we'll stop doing stuff, but I'm hoping to be able to go through all this. That's why I produced the notes. So you can read ahead if you want to. I don't know what your pressures are for the finals. And we need to stop today because it's 21 after. And so I'm going to get off the share screen. Anybody have any comments before I throw you all away?
I'll see you on Friday, Dr. Brady.
I'm sorry, say again?
I'll see you on Friday, Dr.
Yes.
Brady.
Will you
Thank you.
see me on Friday?
I'll try. I'll try to be there in person.
Well, no, you will see me on Friday if you're in class. Will I see you on Friday? That's the question. Anyway, okay, so it's nice to deal with you people. I can't see you, but I'm saying goodbye. Goodbye.